Hello, I want to welcome you to this webinar recording. My name is Candace Owen, and I'm newer to the district, but Derek Rapp and I have been working on this workbook extensively, and we're really excited to get this information out to you and take your questions. Huge thanks to Derek for all of his work on this. We are really excited about the capabilities of this workbook. Derek Rapp is with Peak Stormwater Engineering and has been intimately involved with this project. So this is a re-recording after the actual webinar due to some recording difficulties. However, all the information and content is the same. Just a little fun before we get started. I've looked up Mile High's new address many times online on a well-known search engine. And I noticed after doing that a couple of times that there's actually a review for Mile High Flood District. We have a rating and thought that that was pretty interesting. So diving a little deeper, I found these. 5 stars 3 years ago, excellent service. 6 years ago, 4 stars, my favorite drainage district in town. However, not warranting 5 stars. What can we do for that last star? 5 stars 5 years ago, they're great people doing work. And then this one, 4 years ago, 5 stars. Love urban drainage, but wish you would allow us to move and copy tabs in UD-BMP spreadsheet. Should we have multiple rain gardens on one project and don't want multiple UD-BMP spreadsheets for each one? So this is such a funny forum to put this comment in, but I am excited to say that our webinar today is all about the new capabilities of SCM Design, which is replacing UD-BMP, and how you can have multiple SCMs in one workbook. So really excited about that and pretty funny comment. Really quickly, I want to promote our upcoming office hours. These will be kind of a free format, so please email me with your questions beforehand. And the links are on our website at the QR code to the right. So you'll go to the website, click on the link at the time listed there, and you'll be allowed into a Teams meeting where you can ask questions. And we'll also be posting new content and opportunities as they arise on the website. Just a couple of housekeeping items that we presented in the webinar. And let's quickly go through the agenda. We're going to cover what's changed and also what's stayed the same, an introduction to the workbook and its different components, the site assessment tab, the new site layout tab, and our different SCM tabs. And then we're going to walk through a number of examples, starting with a really simplified EDB and moving through the other capabilities of the workbook. I encourage you to follow along in your own spreadsheet and have that open as we move through the webinar. So this SCM Design Workbook update was precipitated by the update to the Urban Storm Drainage Criteria Manual, Volume 3, Chapter 4. And this was a substantial update to that chapter. It had the last major update that had occurred in 2010, and a lot had changed in that time. Some highlights from the update included a reorganization that consolidates information on common components of SCM, such as forebays and underdrains, in the upfront sections, and then guidance on how to assess the site for ability to use infiltration SCMs, and a discussion on how to incorporate community values. Additionally, grass buffers and grass swales were consolidated into a receiving pervious areas fact sheet, and we added in a manufactured treatment devices fact sheet. So the proprietary devices, as they're typically called, are also incorporated in the chapter and also the SCM workbook. So what's similar? Let's start there, between UD-BMP and SCM design. Only one real change from the SCM fact sheets in the pages within the workbooks, and that's rain gardens to bioretention as a title. But these other sheets should be pretty similar. They have some additional content included and more detail around how to design, but for the most part, they are pretty much the same. One big difference that Derek's going to talk about and that you'll notice is that these sheets are initially hidden. And so you have to work through the site layout page to have those unhide as you're determining which SCMs you're going to use on your site. All right, next up, what has changed? And how the sheets function has changed quite a bit. So we've got a BMP selection tool in UD-BMP, and that was actually removed and sort of replaced with our site assessment sheet. But the BMP selection sheet was really outdated. That chapter of the criteria manual needs an update as well. So that may be that may come back into the workbook in the future. But for now, there's a lot of good information in the site assessment sheet about how to determine your SCM. And so runoff reduction, grass buffers and grass swales were all included in what we're calling the receiving pervious areas sheet. And that follows the chapter specifically. And so we'll talk more about that. Constructed wetland channels were removed. And green roofs and blue roof systems and manufactured treatment devices were added in. So some major changes. The site assessment worksheet walks through questions that help the designer understand what type of infiltration is possible, where step 1 of the 4-step process is possible, and where the site constraints might dictate the SCM that's used. For the site layout worksheet, this is really the hub of the workbook and is kind of the starting point where you trigger what type of SCM you're going to use and dictate your outfalls, to also the ending point where information, water quality, capture volume, and other results is reported back or are reported back to the site layout sheet in a summary kind of format. And then again, this is the sheet that triggers the SCM design fact sheets, so they're no longer visible initially. And finally, runoff reduction calculations are now able to count for that infiltration, that runoff reduction in series above other SCMs or upstream of other SCMs, which is pretty exciting. And then grass swale infiltration is calculated differently than grass buffer infiltration. And that is that's also following along with changes in Chapter 4. So with that, I will kick it over to Derek Rapp to continue our webinar content.
All right. Thank you, Candace. Let's jump in. We're going to start with the introduction worksheet, which is very similar to all the other MHFD workbooks. So if you've used any of the other workbooks before, you'll recognize kind of this intro sheet. One of the first things you want to look at is the version that you're using. And you can see here that we just released this in April of this year. And this is version 4.0. So it's building off of a previous version of UD-BMP. And you can see when we click on the revision history here, you'll see that at 3.07 was the last version of UD-BMP before version 4.0 was released, following the new Chapter 4 updates. So it's always important to make sure that you're grabbing the latest and greatest workbook. We've already received several comments back with information or recommendations on things that we could improve. And so there will be a version 4.01 coming out soon. And we hope that those of you listening today will either provide comments in the chat today or follow up in one of the office hour sessions and provide additional feedback so that we can continue to improve this and hopefully incorporate a lot of those recommendations into the next version update that's released. Like all of the workbooks, we list the purpose and function. Again, the purpose of this workbook is to help in the preliminary stages of designing your SCM. It also, in terms of function, it's essentially designed to follow along with the new Chapter 4 update. So every part of this workbook, especially in the fact sheets, follows along the design procedure steps. So, for example, part 4 of an EDB in the criteria manual will be step 4 in that EDB fact sheet when you're filling it out in here. We tried to maintain that continuity and streamline the process so that if there's any information that you would like to look up or get clarification on in the chapter, it's very easy to go find what section to look in. Another thing that we've done is, from a compatibility standpoint, is try to make this consistent and to be able to work smoothly with MHFD detention. The reason being is neither one of the workbooks can handle everything. MHFD detention is designed to look at rainfall runoff and generating hydrographs, routing those through a detention basin and outlet structure to make sure you're meeting a target release rate or a drain down time, such as 40 hours for a EDB. And the water quality workbook here, the SCM Design Workbook, does not do any kind of hydrograph routing. And so what you can do is you can start your design here. You look at your site layout and moving water to various SCMs and outfalls. And then you can take that tributary area information, plug it into the detention workbook, size your preliminary basin, geometry, bottom width, slopes, and then configure an outlet structure. Looking at the orifice plate and drop structure and overflow for a full spectrum design, and then bring some of those details back into the SCM worksheet and help populate some of those inputs. So we'll go through some of that in more detail later, but just know that we've tried to make those two workbooks consistent and compatible with each other. All right, so how is the workbook laid out? Well, we talked, and Candace mentioned earlier, we've got a site assessment tab and a site layout tab. Both of these are visible as soon as you open up the workbook. So if you move away from the intro tab, you'll see the site assessment tab. And this is optional in the sense that it is not required to move further into the workbook and work on designs, but it is highly recommended. And it may be required by local jurisdictions in terms of a submittal. They may want to know this, but we'll go through what's included in the site assessment in a minute. More importantly is the site layout worksheet. This is the hub, as Candace mentioned, of getting into the workbook, providing the preliminary input, and also summarizing all results from every SCM worksheet that's generated in the workbook. So this is the point where you go in and you define how many outfalls leave your site, what type of SCM are you using to treat the runoff at that outfall location. Once you select an SCM, it is going to generate a corresponding workbook. And what you can see from this double-sided arrow is that once you fill out that SCM worksheet, those results get summarized and carried back to the site layout worksheet. So this is where you generate the SCM worksheets. This is where you fill out and design your SCMs from bioretention to EDB to retention ponds and etc. And then those results get carried back and summarized here because you may have multiple outfalls on your site with different types of SCMs, or even duplicate SCMs such as bioretention located in series or adjacent to each other. Then the next part of this, moving into the yellow box here, is within an existing SCM, you may want to account for runoff reduction upstream of that. And what this allows you to do is go upstream of that SCM and look at the different areas, whether it's DCIA, UIA, RPA, and SPA, and figure out where the potential for infiltration options through buffers and swales, and how do you reduce the volume that reaches the downstream SCM. So it's going to take that information that you generate on that worksheet, it's going to pull it back to this SCM worksheet as the inflows to the SCM. Similar but slightly different is upstream pretreatment MTDs. So these are situations where you may have a high sediment load coming in, and rather than designing a 4-bay, you want to put in, due to space limitations, you may want to put in a manufactured treatment device, such as a hydrodynamic separator. And what this does is allow you to take the tributary inflow information from the SCM worksheet and then move over and work on determining what the appropriate sized MTD would be for this location. But you'll see that that's a one-way arrow. Because this is dealing with peak flows, there's really no volume to be carried back to the SCM worksheet. So that's why we have the one-way arrow there. All right. If we scroll further down on that worksheet, you'll see that we've got the shortcut buttons here. The first is the site assessment. And when you click on that button, it's going to take you to that site assessment worksheet, which we'll go through in a little more detail here in a minute. You've got the button for the site layout worksheet. And what you'll notice on the site layout worksheet, there's a lot of columns available for input. Each column represents a different outfall ID. So it's important to note that you may only need one column here. You may only need to enter input for the first column if you have a single outfall from your site. But know that you can have as many as 100 different outfalls from a project. What this allows you to do is evaluate multiple SCMs within the same workbook. You can even evaluate multiple of the same type of SCM. So you may have something in series. You may have a grass buffer that drains to a swale that drains to another swale, etc. It allows you to do a lot of those treatment train approaches, as well as have multiple outfalls with maybe an EDB on either corner of the site. So as long as you understand that those individual columns each represent an outfall, and that you can generate an SCM for each column. And then finally, there's a button here to show the example site. By default, this is already shown. If you click the button again, you can hide that example site. This is the example we're going to go through during our presentation today. And you'll get a sense for the various components you can add. We're going to focus in on a small portion of the total example. We're not going to go through the entire thing in this webinar. All right, so looking further at the intro sheet, you kind of get a sense for all of the different worksheets that are included. Now, you can't immediately see all these, and they'll be generated as we talked about. So the first thing I want to point out is the worksheets that are in this green box. These are your various SCMs. And so anytime you, on the site layout worksheet, that you create an outfall and you select an SCM, it's going to populate one of these sheets. And what it's going to do is it's going to take the hidden template, for example, for bioretention, and it's going to assign it an ID number based on your design point for that outfall. And then it'll create a copy of that template as a new visible sheet that you can then enter and work on. Similarly, you've got the values in the yellow boxes up here. The first one is your inflows to an SCM. So what this allows you to do is look at RPA, both grass buffers and grass swales, upstream of your SCM, so that you potentially can reduce the amount of volume that reaches that SCM downstream and limit the volume that you have to provide. Now, I want to make it clear that the inflows worksheet, which is SCM inflows from upstream RPA, is the identical worksheet to what you see in the green box in the first one there, the RPA receiving pervious areas. Those are the same worksheet. It's just they're accessed differently, and the worksheet treats them differently as to whether they are discharging directly off-site through an outfall or whether they're discharging to a downstream SCM, such as an EDB or bioretention. And so it's important to note that you can trigger those from either place, either from an SCM or directly from site layout. And then you have the SCM HDS tab. And what this is looking at that upstream pretreatment. It's that lower yellow box. And again, that's just looking at pretreatment acting like a forebay into one of your SCMs. If you were to take the entire workbook and unlock it and show all the tabs that are hidden, you would see all of these templates. What the program's doing is it's taking one of those templates, making a copy, changing the name by adding your ID number to the end of it, and then making it visible. So the templates are always there, and you can use them more than once in the same workbook. But that just kind of gives you an insight into how it's functioning in the background. Okay, now we're going to go into a little more detail on the site assessment tab. What I want to talk about here are the three main portions of this sheet. And again, this is optional. You do not have to fill this out to continue over and evaluate SCMs. But it is highly recommended that you do this early in the project, and certain jurisdictions may require it as part of a submittal. What this does is tell the reviewer that you've thought through a lot of these potential constraints, and you've thought through ways to minimize impacts and evaluate infiltration at SCMs. So in the first section, we're talking about physical site characteristics. And what we want to know here is, what is your total site area? Are you working in a floodplain? Is it a phase development? Is it going to be done in different phases? Are there wetland delineations that have been done? Are there any threatened or endangered species on the site? Continue down a little further. You've got utility mapping. Describe that. Other TMDLs you have to deal with. Are there ways that you can take existing community values and incorporate that into your design. And last is the idea of, are you incorporating full spectrum detention, or is this water quality capture volume only type of site, and you're dealing with flood control offsite in a regional facility? So all of these are kind of open-ended questions, and allows you to provide a lot of information. The more information you provide in doing these questions allows the reviewer, one, to know that you've thought about it and you've either addressed some of them, or or they're not appropriate for your particular site. Hopefully that shortens the review period and reduces the number of questions that you get back. It also makes you think through everything, so you don't get halfway into the project and realize that, oh, we can't do this because we're working in a wetland here and we don't have any way to mitigate that. So again, ways to help streamline the process once you get further into design. If we move down to the second section of the site assessment, this is where we start looking at the step one of the four-step process for runoff reduction. And what this includes is the opportunity to think through and discuss how you're going to conserve any existing amenities, whether that's good infiltrating soils, how you're going to utilize those for water quality purposes, how can we minimize our impacts by not disturbing areas that aren't necessary, and where are there options to redirect runoff from impervious areas across vegetation and promote infiltration. So again, forces you to kind of think through the approach to the project early on, and lets the reviewer know that you've either considered it or are addressing it. And then the final question on here, section 3, is related to whether or not the site is appropriate for using infiltration-based SCMs. And these questions are kind of geared towards the entire site as a whole. What are your dominant soil types on site? If you've got type A soils, you've got a really good option for infiltrating a lot of the runoff. If you're dealing with type CD soils, you still have some potential, but you may need to consider underdrains or consider using a liner. There's several questions on constraints and associated risks. Other expansive soils. Are you dealing with contaminated groundwater? All things that may increase the risk associated with doing infiltration type designs. And there's a couple of geotechnical questions as well. The goal of these questions is to kind of work through this example, or this table 4.3 in the new chapter, looking at both risks and whether an infiltration approach is appropriate. Can you use full infiltration, or should you be using an underdrain, or possibly even a liner as well? And you may even get recommendations to avoid it altogether due to certain risks. You're better off finding a different type of SCM or looking at a different location to treat the water quality. Another thing I want to point out here is that on this site assessment tab, you're going to get asked questions about infiltration-based SCMs on a more generic scale, large scale for the project. Once you've selected, if you choose to use one of the infiltration SCMs, such as bioretention or sand filter, one of the first sections in those fact sheets is going to start asking more details on infiltration. It's going to ask, what are your infiltration rates based on infiltrometer tests, and get into a little more detail to help decide, is this particular location appropriate for this type of SCM? So you're going to see some similar questions and some overlap, but they're going to dig a little bit deeper to make sure that it's an appropriate design based on the site considerations. All right, now we're going to move into the site layout worksheet. As we mentioned earlier, this is kind of the hub of your workbook. This is where you're going to enter your first set of input. Then you're going to create your SCM worksheets, and then you're going to come back here and look at the results at the end, both for each SCM, each outfall, as well as the total for all of your outfalls on the site. So the first step is to determine the number of outfalls from the site. This may be a single outfall if all of the project area drains to a common location, or it may be several columns if you've got an area that has multiple outfalls from the site. You can have multiple SCMs, you can have treatment train approach, and currently you can see about 12 columns, but just know that this expands well out to 100 columns of different outfalls, which is pretty unlikely for any given project site, but we want to make sure that the workbook is not a limitation in what you can design, and avoid having to create a second workbook in parallel. So that is why this expands. So as you fill out the first 12, a new column will appear. Next, for each of those outfalls, you want to identify the total tributary area and imperviousness upstream of that outfall. So for example, if you've got a single outfall, you want the total area draining to it and the imperviousness. The next step is to select an MS4 Design Standard. There are 3 options: the Runoff Reduction Standard, the Water Quality Capture Volume Standard, and the Pollutant Removal Standard. You also have the ability to select none. If you've got a small portion of your site that you're not able to capture, or that is mostly vegetation or vegetated area and just drains off-site, maybe to a curb and gutter, and you're not able to redirect that to your SCM, then you can select none and account for that small area. But for the other options, depending on what you select, there are going to be, it's going to populate SCMs in the next row that are appropriate. And that's based off of this table 4.1 in the new chapter. You'll see that if you're trying to meet the runoff reduction standard, you can either do that through grass buffers and swales, through a green roof, and potentially through bioretention, sand filters, and permeable pavement through infiltration, full infiltration of those. So by doing those, you're limiting the amount of runoff that leaves the site and trying to meet that standard. You'll notice that there's some footnotes in these, potential footnote 1, and you can look at that in the chapter for more detail. From the water quality capture volume standard, you'll see there's a lot more options. So grass buffers and swales are not really capturing any volume. They're just a flow-through type of situation. So those are not, you're not going to have that option if you select WQCV. But you will have a green roof option, potentially a blue roof. You're going to have bioretention sand filters, as well as your sedimentation ones, your retention ponds and constructed wetland ponds and extended detention basins. What you don't have is any of the flow-through devices like your MTDs either. So those are not an option. And then finally, your other option is pollutant removal standard. And you'll see that really the only way to meet that is to either meet it through the high rate filtration devices, both biofiltration and media filtration, or indirectly through capturing that volume, the water quality capture volume, assuming that it's designed appropriately based on the BMP database. If they're sized appropriately and provide the right retention time, then you may be able to meet that pollutant removal standard as well based on that research. So read the footnotes on those more carefully if you choose to try and meet that standard. That being said, once you've picked a standard, you're going to get an available pull-down list in this row. This will turn blue, and you'll have a little arrow here you can pull down and select what type of SCM you want to do. And those could vary from RPA, the rooftop systems, to your infiltration SCMs, your sedimentation SCMs, and your MTDs. You have those various options depending on your standard selected. Once you select an SCM type, it is going to create a new worksheet. It's going to take that hidden template. It's going to give it the SCM name that you selected. That's EDB in the example we're going to do first. And it's going to follow that with an ID number. And that's going to be whatever's in this first row here for your Outfall ID. And that's how it distinguishes that EDB from potentially one at a different location for a different Outfall. Once you've filled out that SCM worksheet, which we'll talk about in the examples, you're going to come back and you're going to look at those results. So for all of your Outfalls, each of these columns, you're going to have results in the corresponding columns. What is the water quality capture volume? What is the reduction based on any upstream runoff reduction, grass buffers and swales? And is there any untreated water quality capture volume from that at that particular Outfall location? And then once you've done all the individual columns, it's going to take all of that information and summarize them down here below for your total site. And this is really helpful for reviewers to kind of get the information they need to make a decision on whether or not you've met that standard. The workbook's not going to explicitly state if you've met the standards or not, because there's so many ways that can be done, and there's lots of exceptions and variations. And so that is up to the engineer and the reviewer to determine whether or not it's been met. But hopefully the information needed to make those decisions is provided here at the summary level. All right, we're going to move now into the first example. And this is looking at an existing site where we're going to go in and modify the site. This particular site has a total of 10 outfalls. You can see these black boundaries indicate an outfall draining in different directions. So you got the southwest corner, the northwest corner. This is a central location that doesn't discharge off-site. It takes rooftop and infiltrates it. You've got the eastern site. And that's what we're going to focus on for this example, is we're going to focus on this area here that drains to the east end of the site. And where it drains to is an existing detention basin. Note I say detention basin, but not extended detention basin. That's because this discharges through an 18-inch corrugated metal pipe. There is no orifice plate that ensures a 40-hour drain down time. And so what we want to do as part of this example is determine what the upstream inflow area is, what is the imperviousness, total area, determine what that water quality capture volume needs to be, and then size and outlet structure to discharge that over a 40-hour period. So that's what we're going to step through first. And we're going to do that by following the process in the new Chapter 4 and all the design steps in that fact sheet. So let's go ahead and get started on that. We zoom in a little bit closer. Let's take a look at the nuance of this particular drainage. What we've got here is some rooftop, and that is the blue flow arrows are indicating the surface flow direction. These are directed to roof drains, which go underground below a courtyard, discharge through pipes. These orange dots here represent storm inlets. That's an area inlet. And then that discharges into a concrete channel, which discharges into this pond here. We've also got some sump inlets in this location. This is a loading dock that sits below grade that are then connected to an area inlet and down to a pipe discharge into the proposed pond. You also have some sheet flow coming off of the parking lot into the pond. And so what we want to do is define what is the imperviousness of this area and what is the total area. And that's a GIS exercise. One thing that I want to make very clear here is that as part of this process, when we're doing everything that drains to this outfall, we need to include the SCM footprint itself. And the new update to the Runoff Chapter 6 in Volume 1 is they've added impervious values for various SCMs. And the EDB, the assumption for EDB is that it's 25% impervious. So that should be included in your area-weighted imperviousness. And so here we have roughly 2.8 acres and about 72% impervious. If we use GIS to go in and break this up into impervious and pervious areas, at a simple level, we're seeing we've got the rooftop and all the parking lot area and the concrete channel as being impervious. And that's all in red. We're calling that directly connected impervious area because it all drains directly to the pond. The yellow is SPA, so that's separate pervious area. Because in this first example, we're not going to account for any infiltration of the impervious surfaces. So even though you might be able to redirect some of this across grass buffers, right now we're not getting credit for any of that. We're just doing a standard, typical approach that's been done in the past. So we can demonstrate later the benefits of getting credit for UIA RPA pairs. All right, so let's go in and set up this site. If we look at our site layout worksheet, the first thing we need to do is provide some input. We give it an outfall ID, and we call this one E for East. Again, we're just trying to shorten these names. We have our total tributary area, that's that roughly 2.8 acres, and our 71.6% impervious. Next, we're going to select a design standard. Because we're doing an EDB, we're trying to meet a 40-hour drain time, we're meeting that WQCV standard. What that's going to do is going to create a pull-down list within the SCM type row, and we're going to select EDB from that list. When we do that, it's automatically going to create a new worksheet from the hidden template called EDB_E. So it's taking the SCM type we selected, and it's adding a suffix, which is the outfall ID, and it creates that new worksheet. So we've now generated a new tab within our workbook. Currently, the results are all empty. We know our default water quality capture volume. That's just calculated based on area and imperviousness, and our 40-hour drain time, which we already know from this limited information. We know what our default water quality capture volume is. But we don't have a design water quality capture volume here yet. We've got to go and design that in this EDB workbook. And then once we fill this out, it'll bring the results back over. So if we flip over and look at the EDB workbook, you can see that it's already populated the outfall ID. So that matches this worksheet, this new tab is matched up with this existing column here for E. So any work we generate in this new workbook, those results will get carried back into this column and summarized here. So let's jump over to this and start working on the first section, which is inlet and forebay. And for anybody who's worked with UD-BMP in the past, this is going to be the new part of each fact sheet, is this first section where we're dealing with inflows. And we're talking about how does the water get into our SCM. And that's a big part of what's changed in the updated Chapter 4, and the upfront section is looking at those inflows. So let's dive into that in a little more detail. The very first question that you get is related to, is runoff reduction used upstream? Now, as I mentioned, right now we're just looking at DCIA and SPA. So we're going to select no for this. And when we do, what that's going to do is when we hit no in this question here, this first row is going to turn blue for us. And that allows us to define our inflow points. But for our sake, what we're doing, we're going to just assume that everything comes in at one location. When we come back and look at the runoff reduction later, we'll break it up into some more of those inflow points. But really what we want to look at is both the pipe and that concrete channel come in the southwest corner, and that's where we're going to focus our inflow point. So we said no, there's no upstream runoff reduction. It creates this first row. Then when we fill out one of these, it will start to enter in these additional blue cells that we then have to fill out. So one thing that I really want to make clear here is when you have multiple inflows to the EDB, we only want to know the upstream area and imperviousness at that inflow point. So we do not include the footprint of the EDB here. So you can imagine if we had 5 different inflow points, we had 5 pipes coming into this pond, that we would only want to know the area upstream of that inflow point so that we could determine the appropriate forebay size or what the whether or not we need energy dissipation or how the sheet flow is coming in at that location. So this area and imperviousness excludes the footprint of the EDB. It only accounts for everything upstream of that particular inflow point. All right. Next, you have the question about, will there be pretreatment with a sedimentation MTD? Currently, we're going to say no. We'll come back and revisit this in a later example where we can look at upstream pretreatment using an MTD, and we'll talk about that new MTD fact sheet and how that is used in the workbook. The next section for inflows is to look at how does the flow enter the EDB. And in this case, we've got flow coming down that concrete channel and pipe. So we're just going to look at, either one of those would be the same, right? We've got concentrated flow coming in. We're going to select pipe here, and we've got riprap as energy dissipation. From a forebay standpoint, because we're so small, our impervious area is less than 2 acres, we can use a concrete sediment pad as opposed to going through a full forebay volume design. If you had much larger areas, you'd want to do a bigger forebay, and then you would need to provide the actual design forebay volume based on some recommendations, and actual depth based on the recommendations by the program, and then determine what your rectangular width would need to be for the release notch to drain it out in 5 minutes. So that information for a small site is not necessary, but as your site gets larger, you would need to fill in these cells. And the program will determine, based on your selections, which cells to block out and which cells you need to provide responses to. So it kind of steps you through the required information. Now, what you may notice is that we've got sections A, B, and D. For purposes of fitting this on a single presentation slide, I've dropped C, which was sheet flow. And so for sheet flow, you've got similar questions. If you were to select sheet here, you would have fill out some portions of section C. The options include curbless pavement, slotted curb, or level spreaders. And for concentrated flows, you can look at downspouts from a roof. You can look at curb openings, pipe, outfalls, grass swales, channels. There's a lot of different ways you can do those. And depending on what you select for your inflow feature, you're going to have to answer different questions. So for example, if you selected curb opening, you would need to go provide the depth of gutter flow line for that curb opening. You would need to provide the width of that curb opening. And so those 2 cells would be populated. So depending on what you select for your type of inflow feature, you have to populate different responses here for the input. If we continue down and scroll down on the EDB worksheet, things are going to start looking a little more familiar for those of you who have used UD-BMP in the past. So section 2, and again, this is number 2 in the design steps for an EDB on the fact sheets in the chapter. So the numbering system is consistent here. So step number 2, design storage volume. What this is going to do is it's going to pull over your total area, your total imperviousness from the site layout sheet. So this includes all of those inflow points above. So you've already defined those. In this case, we just had a single one. And it's going to include the EDB the total areas based on what you entered on the site layout sheet. And it's going to calculate that default water quality capture volume. This is the same number you see on the site layout sheet. Now, because we selected no for question 1A, which was, is there runoff reduction upstream, 2D and 2E are going to be grayed out. They don't apply. But if you were to select yes there and look at upstream runoff reduction through buffers and swales, these will be black again, and you'll get some information here. And we'll talk about that in the next example. The next question is, what is your actual design geometry? And this can vary. It doesn't have to be the minimum requirement that you get up here, 2916. And so this is where you can kind of jump over and use the detention workbook. So in this example, what I did was I took the information for the total tributary area. I estimated my flow path and slope for length, accentuate, and slope, plugged that information into the detention workbook, and was able to generate inflow hydrographs, determine my preliminary basin geometry, size and outlet structure to both release the WQCV in 40 hours, as well as meet full spectrum detention requirements for the EURV and 100-year release rate. And so what I did is took that information from the detention workbook and brought it back here. It came up with a volume based on the geometry of the pond of 2930 for my WQCV, slightly greater than what I needed, so that's sufficient. It also accounts for what is my depth, a volume associated with EURV and 100-year storage. So just documenting some of that information from the detention workbook so that a reviewer can check for consistency between the two and make sure that there's no typos or mistakes going back and forth between the two workbooks. What you'll also get out of the detention workbook is that orifice plate dimensions, which we'll talk about on the next slide or two. What does that outlet structure look like? All right, so if we continue down through the fact sheet, number 3, these start to look really familiar if you're familiar with UD-BMP. So there's simple questions. What is your basin length to width ratio? And in this case, it's 5. We kind of got a long, narrow basin along the edge of that parking lot. We can provide some descriptions of that. We can provide side slopes for that basin. We can describe the low flow channel. And one thing you'll notice is that in previous versions, the recommendations were concrete trickle channels. The new chapter has moved into vegetated low flow channels. That's providing less maintenance and better water quality benefits. So we provide some information on the low flow channel as well as the basin bottom slopes to ensure positive drainage throughout. Continuing down, what is your initial surcharge depth? What is your outlet structure? How is that configured? Do you have a micropool? Is it internal or external? What are the dimensions of that micropool? What is your orifice plate opening? And you can see here that we've got 3 rows of half-inch circular holes roughly 18 inches apart. This is all based on MHFD detention and pulling that information back over. What this does is help you figure out what does my trash rack need to be. Based on those dimensions, I want to use a well screen and bar grading. If those dimensions are larger, you can get away with just bar grading for your trash rack. And how is that configured? Is it a vertical or is it sloping? And then you also have the option to go in and describe some of the results from your overflow structure, your drop structure, and outlet pipe from MHFD detention, and document that here as well. And if you continue down through these, you've got your overflow embankment. Is there a vegetation or landscape management plan? What are some things that need to be considered? Describe that you have considered those for the reviewer to know that it's been addressed. Maybe you can reference specific details and drawings, things like that. Also, maintenance access. How are you going to get to the basin to clean it? How are you going to get to the outlet structure to maintain that? So once you've finished filling out that EDB fact sheet, and again, it's that first section, those inflows, where you're looking at sheet flow, concentrated flow, are you doing upstream runoff reduction? That's kind of the new piece for this EDB workbook. As you continue to move down through it, it becomes much more familiar with the old fact sheets and follows a similar concept. It's just they may be reordered a little bit based on the new Chapter 4. We're following those design procedure steps number by number. So when you come back to your site layout worksheet, and it's going to bring those EDB results back. So what you'll see is that because we selected no for upstream runoff reduction, there is no reduction in our water quality capture volume. So our design volume needs to meet that. And in this case, we're at 2930, just slightly over the minimum requirement. And because we've exceeded that, there is no untreated water quality capture volume. Now, you could continue, you could create a new SCM, another EDB in the opposite corner of the project and continue this process and make sure that meets it. You may have areas that don't have any treatment, and then you're going to have some values in this bottom row that are untreated. So that's how those results get carried back. So in this case, it's pretty simple. It just brought back our actual design volume. And because we only have one value here, you're going to see that that's the total down below as well for the entire site. But as you add more, this is going to start summing up all the individual columns. So let's now go back and revisit this example, but look at how do we incorporate runoff reduction? How do we get credit buffers and swales and infiltrating runoff volume before it reaches the SCM? And we'll step through this project. So here's what we started with. We just had impervious areas delineated. But now what we want to do is go in and look at opportunities to route impervious across vegetation and get infiltration credit. So here's where we use the 4-cover land use model. So we have our DCIA still, but some of that DCIA becomes UIA, unconnected impervious area, if we can route it across a receiving pervious area and allow time for infiltration before it reaches the downstream EDB. And then we still have some SPA. So let's kind of step through what we're doing here and changing. If we look at the rooftop, this is impervious area, but if we can convert this concrete channel, E10, into a grass swale, shallow, broad grass swale, then any runoff that flows through that swale has an opportunity for infiltration. So this then becomes UIA, and this becomes the associated RPA, the swale. Same thing can be said for this parking lot. This parking lot E5 is going to drain into that inlet, get discharged into the swale, and you're going to get infiltration potential as it travels through this swale to the EDB. We can get additional credit using a grass buffer. So here we've got some parking stalls in E7 that are going to sheet flow across a grass buffer E8 and into the swale. Now, it's very important that these are delineated appropriately. In this situation, the grass swale, the RPA for the grass swale should only include the bottom width. So that's going to be equal to the flat bottom width of the grass swale times the length of that swale. And that's going to be your RPA. For the buffer, in this situation, this grass buffer acts as the northern embankment to that swale. Whereas E9 on the south side, there's the embankment for this grass swale on the south side. But because there's no imperviousness draining across this south embankment is just considered SPA. Whereas the north embankment is RPA because you're treating impervious area sheet flowing across it before it hits the bottom of the swale. So here you get credit for infiltrating some of this runoff from the parking lot into the buffer. And then a treatment train approach, you also can get credit for some of that flow as it moves down through the swale. And that's one of the advantages of this new workbook is that it allows you to get credit for these treatment train approaches. And again, the E1 and E2 drain through this. If we look up above, you've got impervious area that is in a sump at the loading docks. That's all being picked up in these inlets, these two, and then you've got some of the parking lots picked up here by this inlet. That's all being piped directly, so that stays as DCIA. However, the remainder of this parking lot is just sheet flow into the EDB. So as long as you can maintain uniform sheet flow, you can run it through this vegetation stretch as a grass buffer before discharging into the EDB. And so you can get some runoff reduction credit from E19 and E20. That's a UIA RPA pair as well. For our purposes in this example, we're just going to focus on the one flow path. So the example in the workbook includes it all, and includes the entire site for that matter. But for purposes of time, we're going to try and just focus in on this one flow path of the roof in the parking lot and this parking lot across the grass buffer and through this grass swale. And we'll go through that example and set it up. So let's start there. What is the first step? The first step is to select yes. So we want to go in and say for number 1A, under inlet and forebay, we want to say yes, runoff reduction is used upstream of this EDB in order to promote infiltration. When we do that, it is going to automatically generate a new worksheet, and it's going to add the suffix inflows to the end. So you see the paired worksheet is named here. This is the new tab it creates. What it's doing is it's taking that RPA tab, the hidden RPA tab, and it's renaming it. It's giving it the prefix, associating it with this EDB, and it's renaming RPA to inflows because these are runoff reduction inflows upstream of an SCM. So they're inflows to our EDB. So this is EDB SCM at the eastern outfall, and we're now addressing inflows upstream. One thing I want to point out is that previously this first row had turned blue when we selected no. But now that we select yes, the program is expecting you to go here and define what your inflows are. And then when you fill it out, it'll automatically populate this table with that information. So you can no longer enter these values on your own. You need to go to this worksheet, enter the information to generate those values, and they'll be carried back to your EDB worksheet and populated here automatically. So let's jump over to this new RPA worksheet. And in this case, it's an inflows RPA worksheet because they're not discharging directly off-site through an outfall. They're discharging to another SCM. So they're in series. And so we call it the inflow sheet. So what do we do first? Well, we want to identify that it is in fact paired with that EDB at the eastern outfall. So it's going to automatically populate this, and it's going to fill out this first column. So the first column is going to tell you where's the outfall, what type, it's an EDB, and then most of the rest of this is going to be grayed out until you get to the very bottom, at which point there'll be some summary results in the last section. So stepping back and looking at this worksheet, the RPA worksheet, is broken into 4 parts. The first part is information that applies to the entire site when you're doing the floor cover land use model for DCIA, UIA, RPA, and SPA, and information that applies to both buffers and swales for number 2, 3, and 4. The next section is specific to just grass buffers. So part 2 of this is just grass buffers. Further down below, if you scroll down on the worksheet, you're going to get just grass swales. And then the bottom, section 4, is the summary results of the entire sheet. So you've got universal input for both buffers and swales, and you've got a buffer section, just a swale section, and then results from both. So in this first part, we want to go and take our GIS information and populate this first row. We want to identify all of those different area types and give them a design point ID. One way to think of this is like a swim model, right? So EPA swim allows you to have various subcatchments, different areas within your watershed. Each of those are then connected to nodes, which are routed downstream to a downstream node using a link. So what we're doing here is we're defining all of our nodes and assuming that if we can know what the upstream node and the downstream node is, that's how that link is connected. And the program is then going to do calculations to accumulate area and runoff moving down through there. So as we step through this example, hopefully that becomes a little more clear, but as we're doing it, I want you to think of it as a swim node if you're familiar with swim, of nodes and links. We're connecting upstream nodes to downstream nodes and routing all that runoff as it accumulates down through our system. So let's do that for our example. And again, we're just going to focus on this lower tributary area here. So the first thing we want to do is identify the design points. And by design points, we want to give each one of these areas a name. So E1 roof, E2, E3, E4, etc. And we also want to give those, identify what area type it is. So we'll walk through each one of these within the black boundary. So E1 roof is unconnected impervious area because it drains through this RPA grass swale here. So E1 roof is UIA. E2, E3, and E4 are all SPA. So E2 is considered SPA. And the reason this is not RPA is because these roof drains drain underneath of that vegetation. This is actually a courtyard that's elevated with a retaining wall around it. And so you don't want this rooftop drainage draining into this courtyard area and potentially flooding that and backing up into the building. So the rooftop drains go underground. There's an area drain that collects this courtyard area, and they both drain through the storm system and discharge into the swale. So E2, E3, and E4, our SPA areas, are all draining down towards the swale. Our parking lot area, E5, is all collected right at this inlet. Some of it goes into that one, but they all collect at this design point. So that's your E5 design point. You've got E6, which is SPA at this small little parking island here. It's draining into the swale. You've got E7 and E8. So this is a UIA RPA pair. You've got parking stalls here draining into a grass buffer. That grass buffer then drains into our E10 grass swale. And you've got this SPA here that also drains into the swale. So now that you understand the different design points, we've given each of these areas a design point ID, and we've given it the type of area it is, whether it's UIA, SPA, RPA, either buffer, in this case E8, or swale, in this case E10. We've identified each of those. But now we need to make the connections, or those nodes and links. How does one drain to the next? And you can get really discretized in this. You can get a lot more detail, or you can try and simplify it and say, what is the next relevant downstream point that it's going to connect to? And that's what I've done in this case. So we're going to choose a valid downstream design point. It's important to know that you cannot pick a value here unless it's already been created in row 1. And you can't have a design point drain to itself. So I could not pick E2 here. You would get an error and it would reject it until you have to use something different. And you can't pick E27 because that does not exist in the first row. So you need to pick a valid input value for your downstream design point. So as we move through this, our roof, E1, doesn't drain to E2, right? It's going underground. It's going below E2. So the next real point that it hits is this magenta E5 parking lot. It's that design point associated with it. So E1 essentially drains to E5. E2 also drains to E5. E3 and E4 are sheet flow. They're SPA. They technically don't produce any runoff. We'll talk about that in a minute. For a water quality event, they don't produce runoff. But those also drain down to this common design point. And then E5 at this design point, what does it drain to downstream? Well, that point is going to drain into your swale. So E5 is going to drain to E10, our swale. E6, this little parking island here, also drains to the swale. So E6 also goes to E10. But then we look at this UIA RPA pair. E7 drains to E8. So we've got the UIA parking lot stalls, drains into the grass buffer, E8. That buffer then drains into the swale, E10. So here's your swale. And you've also got this area to the south of the swale, E9, which drains to E10. So that's how you identify your upstream and downstream nodes. And that allows the project then to accumulate area-weighted imperviousness, and runoff volume at every one of those design points. And I'll explain how those are calculated down below. Once you've done those first 3 rows, you then need to go in, once you've selected the area type, I should say in that second row, it will create blue cells where appropriate. So if you pick UIA, you then have to enter a UIA, an unconnected impervious area. If you pick RPA buffer, you have to enter an RPA area. Now, the ones I want to really focus on are these areas are what's really important. So you can see for the impervious areas, you've got your rooftop, just a little over 20,000 square feet. You've got your parking lot here, E5 is about 10,000 square feet of imperviousness. These parking stalls are about 4,000 square feet of impervious. Excuse me. And those are all draining down. But what's really important is delineating the RPA areas appropriately. So for E8, this grass buffer, you want to make sure that you only delineate the area that is actually receiving sheet flow. So in this case, if you can uniformly distribute runoff from this UIA across this entire interface width here, then you can account for all of this as being RPA. And you'll notice that it's not uniform in shape because this channel kind of bends. And so you're looking at an average length of that buffer as opposed to a uniform length of buffer. The width is really what's important here. And that helps you determine what that area is for the buffer. Similarly, in the swale, you want to make sure you're not accounting for the embankment, so you're only accounting for the bottom width. So in this case, this value of 1880 should be equal to the width of your swale at the bottom, just the bottom width, multiplied by the length of that swale from the inflow point to the discharge at the EDB. And so that number needs to be appropriately applied. Okay, let's go back to the actual worksheet and let's move down into the further columns. As I mentioned earlier, we need all this information to figure out what the total tributary area, imperviousness, and runoff are coming through our buffer and swale. But as we continue down through this worksheet, we're only designing the buffers and swales. So we're really only filling out columns 8 and 10. Okay, so this is what we need to focus on is columns 8 and 10 as we continue down this worksheet. So the second question here is, how are you going to protect that RPA? So we want to make sure that vehicles aren't driving over it and compacting it, reducing the infiltration capacity. So you have a couple options: wheel stops, markers, fencing, etc. In this case, we selected slotted curb to act as both a barrier as well as a way to ensure uniform sheet flow. Next, we want to define the soil type percentages, and that allows us to look at infiltration rates. So type CD soils have the lowest infiltration rate, but you're still going to get some credit for that. And then the fourth question here in the first section is vegetation type and irrigation type. You may be using seed originally, or you may be planting sod or plugs. In terms of irrigation, it may be a permanent system or a temporary system. This is just a way to think through this stuff early in the project and make sure that it's designed and put on the plans appropriately so that contractors understand what they're doing. All right, let's move down into the grass buffer section. And I apologize for the scale of this in order to fit it on here. Some of it's pretty small. But what I really want to point out is that we're only focused on column 8 because if we go back up and look at this, column 8 is our buffer. When we look at swales later, it'll only be column 10 that we need to fill out. So looking at column 8, we said we're going to use slotted curb. When we select that, it's going to ask us 2 more questions. What is your spacing between the slots and what is your slot opening length? So we enter in those values. It's going to automatically calculate your total area of the pair. So it's going to look at the UIA in that adjacent column up above and add it to the RPA in column 8 and give you your total area combined. What is the ratio? You've got 2.3 times as much imperviousness as you do grass buffer. So that's your ratio there. And that's still a very reasonable ratio, and you'll see in the results in a little bit. Next, we need to provide the interface width. And in this case, that interface width is defined, starting right here at the boundary between the slotted curb and the grass buffer in the direction perpendicular to flow. So going down towards the top of the picture, this is the interface width. How far is that impervious area being spread out, uniformly spread out across the width of the buffer? So in this case, we're roughly 205 feet. If you remember, the swale is about 230 feet, I think. But we're not able to utilize that entire area because we've got some parking islands, etc. So our interface width is about 205 feet. Now, what the program will then do is looking at the total area the RPA area up above and the interface width, we get an average buffer length of about 9 feet. As you may recall, it's not uniformly 9 feet, but that's your average across the total width. And that's used to help determine the residence time and flow path across that buffer and how much volume we can infiltrate. And I'll talk about those equations in a minute. Other information you need to provide is what is the slope of that buffer. So you're going to provide your slope. If it's really steep, you may need, and very long, you may need additional level spreaders to ensure uniform flow is spread out, that it doesn't start to create rills and gullies and start to concentrate again. So typically, a single level spread at the upstream end should work, but for long slopes, you may need to add additional ones. You also want to talk about the vertical drop. That's what you see here, number 2. So you're coming through that slotted curb, 3 is your vertical step, and have that little mowing strip provided so that vegetation doesn't grow up and clog the holes and back water up into this parking lot. You want to make sure that it freely flows, drops out. You also have a maintenance path there to clean up. You can run a shovel down and clean up sediment along that path. The next step is calculating the actual infiltration that occurs in that buffer. Now, this is directly from these equations, which is exactly the same. No changes have been made to this from 2018. So this is what you would have seen on the runoff reduction tab in UD-BMP. This has not changed. And what it's doing is it's taking a bunch of swim analyses that were done on 1,000 different configurations of rainfall depth, area, length to width ratio of the buffer and UIA. What is the slope across the buffer? What is your imperviousness upstream? Taking all those factors into play, there's an equation that then generates your runoff in inches. And that's the runoff in inches that's leaving the buffer. So that accounts for what has been infiltrated. So in this case, you've got 71 cubic feet of runoff leaving the buffer from the UIA RPA buffer pair. If you go back and you look at what's actually running off of the UIA itself, you'll see that you have 170 cubic feet. So you essentially get a runoff reduction of 99 cubic feet, leaving you with just the 71 on the other end of the buffer that drains into the swale. So you've got roughly a 60% reduction from the parking lot, those parking stalls there, just draining across that short reach of the grass buffer before it hits the bottom of the swale here. All right, so now what we want to do is we've looked at the grass buffer component of this area, and now we want to look at the grass swale. And the first thing the program is going to do is look at everything upstream and calculate the total area tributary to it. That's going to include the rooftop, all of those SPA areas. It's going to look at the parking lot upstream. It's also going to account for those parking stalls and RPA draining in laterally. What is that total area and area-weighted imperviousness draining into the grass swale? So how much runoff should we expect in that swale? The next thing it's going to want you to define is what are your swale inflows. And in this case, we're looking at the pipe coming off of the parking lot there and the rooftop drains, that pipe discharging into the swale. Yes, there's a little bit of runoff coming in from the sides from our grass buffer and SPA, but the majority of that runoff is coming in from the pipe. So if you wanted to, you could go back and break the swale. You could look at it as additional design points, but the majority of that flow is coming in at the upstream end. And so we're going to define that as our primary inflow. Again, what we're focused on here is what do we need to do at that inflow point? And, in this case, we've got a pretty small area, well less than 2 impervious acres. So a concrete sediment pad and the natural swale vegetation, we're planting sod, that should be sufficient to handle that inflow coming in. Now, there's some other options you could pick for the swale inflow in a different design. There's level spreaders, downspouts, curb openings like we talked about earlier. All right, next you have to define the swale cross section. And this is where it's really important that those dimensions match what you entered for RPA up above. So in this scenario, we have an 8-foot bottom width and a length of 235 feet. So that you multiply those two and you get 1880. If this is not equal to what you entered for RPA above, that cell will turn red, and it's a flag to make sure that you're consistent and that you're only defining your RPA as the bottom width of the swale, the bottom area, of the swale. All right, the next step is to look at the slope along the direction of flow in the swale. And if you've got a really steep slope, you may need to provide drop structures to bring that down to a flatter slope for stability purposes. And another question it's going to ask is underdrain. And it's really important that you know if an underdrain is included under a grass swale, you will get 0 runoff reduction credit, because although it's infiltrating through the surface of the swale, it's being picked up in the underdrain and just discharged downstream at the same point. So grass swales should not be designed with underdrains when trying to achieve runoff reduction. The only time you would need an underdrain is if it's really flat and you've got ponded water. But if water's starting to pond in that swale anyway, you probably have really low infiltrating soils to begin with, so you shouldn't be getting runoff reduction credit anyway. So just note that if you do include underdrains, you will not get runoff reduction credit in your grass swale. Continuing further down into the grass swale section, the first part is looking at the total runoff. What this first row looks at is the total tributary runoff, disregarding any kind of upstream credits. When you move to the reduced tributary runoff, what that's going to look at is there any RPA upstream in that treatment train. And if you recall, our parking lot stalls draining through the grass buffer into the side of the swale, we had a 99 cubic foot reduction. And so what the swale is actually going to see is only 1,500 cubic feet. Then we want to know how much of that water that flows through the swale is infiltrated. And this is where we differ from the old UD-BMP workbook. This calculation of infiltration through the bottom of the swale is different because those original equations for buffers were developed for sheet flow, shallow, crossed, uniformly distributed. What we've got in a swale is deeper flow that's concentrated and is moving quicker across the surface. So we had to generate a different approach for accounting for runoff reduction in swales. And the way we do that is a very simple equation where we look at the soil type and we find out what the saturated infiltration rate is. So for a CD soil, that's a 1/2 inch per hour. And we look at that over a 2-hour storm distribution, which is the typical storm distribution that was evaluated by the district for all design events, typically for smaller basins. So over that 2 hours, a 1/2 inch per hour, how much of that runoff volume can infiltrate through the bottom area? And that's your volume infiltrated. In this case, it's 157 cubic feet of runoff is infiltrated, leaving the difference of 1501 minus that at 1344. That is what's leaving the swale and entering the EDB. So that gives you a runoff reduction of 10% in that swale. Of the volume that comes in, 10% is infiltrated and the other 90% discharges to the EDB. Now, the remainder of this grass swale section is really focused on channel stability, and it's very similar to the old UD-BMP workbook, where we're looking at if you were to plug in a 2-year design flow, is the channel able to convey that slow enough and at a shallow enough depth that you should get water quality benefit and that the channel doesn't degrade? And in this case, we're checking, is the velocity below 1 foot per second? And it is. And is the flow depth below a foot? And here we're only around 4 inches deep. So that's a pretty good design. We want to ensure that we have broad, shallow flow through our grass swales in order to get maximize our infiltration potential. And so at the end of this, we're just checking Froude number for stability, making sure that those values are low enough. All right, so that takes care of the grass swale section. Now let's move into the summary results. And what this is going to do is it's going to sum up all the results for both the buffer and the swale and every design point in that swim node network. So what I'm going to do is I'm going to step through each of these results for each column and explain how the program accumulates and adds them up in each column. So these are color-coded. So you recall the roof, we're using magenta for the UIA. The roof is 100% runoff, and that's your runoff volume. There is no reduction on the rooftop. E2 through E4 are all SPA, and for a small water quality event of 0.6 inches, all of that rainfall will infiltrate the surface, and there's no runoff generated from the SPA. When we move downstream, this is not just the runoff from the E5 parking lot. This is the cumulative runoff of the roof and the parking lot draining to that last storm inlet right before it discharges into the swale. So this is the total area, or total runoff, of both the rooftop and the parking lot just upstream of the swale. So that's your, and there's no runoff reduction in that upper part, so that's your total runoff entering the swale at the pipe outlet. E6 is another SPA, that small island that produces no runoff in the water quality event. And then E7 and E8, those are our UIA RPA buffer pair. So E7 are those parking stalls. They generated 170 cubic feet of runoff. By the time they make it across the grass swale, they've infiltrated almost 60% of it, and there's only 71 cubic feet of runoff from this parking lot area, this UIA. Only 71 of it reaches the grass swale, E10. Again, E9 is just SPA on the south bank of that swale. And then E10 is going to be the total runoff from the parking lot and the rooftop. So those are already summed up in E5. So E1 and E5 are summed up here. And then E5 and what's coming off of the buffer in E8 are added to the direct rainfall on the swale. So we have to account for rain that falls directly onto the swale, adding into that total volume flowing through the swale. And so that total is 1,600, as you recall from the grass swale section above. But we had the 99 CFS reduction from the buffer, and then we get an additional infiltration volume, which I think was like 157, something like that, through the bottom of the swale. So our total reduction by this point is 255, leaving only 1344 that discharges into the EDB. And so if you look at this last column, you'll see that it matches the first column because we only have one inflow point that we've defined to this EDB. Now, if you had multiple inflow points, this first column would represent this inflow point plus the other inflow points, and it would account for all of that inflow and total runoff volume entering into the EDB. So that's how this worksheet is going to sum up those inflows and track credits for runoff reduction through infiltration. And again, that's the summary of those results. That is what's going to be carried back to our EDB worksheet. So if we go back and look at our EDB worksheet, this information is going to get plugged into the inflow section. So let's do that. What we just focused on was E10, and I'll talk about these in a minute. This is the full example shown in your workbook. For E10, total area tributary to that inflow point, this is the default water quality capture volume. We just mentioned that we had a reduction in runoff volume due to the grass buffers and swales. So the total water quality capture volume required based on this inflow point from the swale has been knocked down from 1182 to 927. Now these other outflow points, other inflow points to the swale are looking at the rest of the site. So E11 is a small SPA that drains in. E21 is the embankment on the east side of that EDB draining in. Again, those are SPA, so there's no runoff in terms of the water quality event. And then E16 is that loading dock area that drains through the pipe. That discharges directly into the pond, so there's no runoff reduction. And E20 is the portion of the parking lot that was magenta that sheet flows across the buffer into the pond. So if you want a little more detail on these individual inflows, you can go back and look at the example in the workbook itself. But that's where these come from. And so that buffer coming off the parking lot that flows directly into the EDB, you're getting a credit of 220 cubic feet of that runoff volume, or that credit to that towards that water quality capture volume that's required. So that would be your total. These three summed up would be the total water quality capture volume as required in that EDB. So what I'm pointing out here is that up to this point, there are no blue input cells. This is all being carried back from the Inflows worksheet. It's not until you get down to here on this row where it asks you if there's upstream pretreatment that you have the option to enter a value. And in this case, again, we're going to select no, we're not focused on that at this point. Let's talk about that in the next example. So if we scroll down, again, this is the EDB worksheet. We've jumped back from RPA to EDB. We've carried these results back, and now we're moving down in the worksheet. So for section 1, we now need to fill out what are the inflow conditions. And I mentioned that parking lot that sheet flows directly to the EDB across the buffer, this is where you have to fill out section C, the for sheet flow. Again, we would be using slotted curb. Those are your curb opening dimensions, and the drop structure and mowing strip. For the swale that we just focused on, we have a swale, the vegetation at the outfalls, how we're going to dissipate on that energy coming into the EDB. And again, we don't need a forebay. We're just going to use a concrete sediment pad at the outlet of that swale to facilitate maintenance. Similarly, we have that pipe outfall coming from the loading docks. We would use, because it's more concentrated flow, we could put some riprap at that pipe outfall, as well as sediment pad for dealing with maintenance. Okay, moving down into section 2 now, what I want to point out is that we now have section D and E are not grayed out. We've carried over the total water quality capture volume reduction due to the buffers and swales leading into the EDB. And we've been able to reduce the required water quality capture volume by 16%. So we now only needed 2,400. Now, I have not gone back to MHFD detention and rerun that program using this, but if you want to get credit for that runoff reduction, that's the step you need to take. So what you would do is go back to MHFD detention, and for your water quality capture volume, you would override the default calculation for the tributary area, and you would use an override value of 2441, and then you would rerun your hydrographs through your redesigned basin volume, and you'd come up with a new orifice plate configuration, different spacing, and different orifice size holes, because now you have less volume that you have to trap for water quality capture volume. So that is how you take advantage of the upstream runoff reduction. And in this case, we're only getting 16% because we're working on an existing site with constraints. But if you start from the beginning of a project and you can incorporate more UIA RPA pairs and limit the amount of volume that reaches it, you could easily get up to 40 or 50% reduction in that volume and cut the size of your EDB in half in terms of the water quality capture volume size. Where that really comes into play is if it's an on-site facility where you're dealing with flood control downstream, you can really minimize and get credit for that runoff reduction. All right, let's take a few steps back, and now let's evaluate pretreatment through a hydrodynamic separator. And so what we want to do is look at this example, and where we have the pipe outfall from these loading docks. Let's say we have heavy sediment loading up here. We want to capture all of this, and rather than just have riprap or concrete sediment pad, the outfall for that, let's go in and add in a hydrodynamic separator and account for pretreatment before it enters the EDB, and use that as a maintenance feature so that we can pump that out as opposed to having to clean up the facility if we've got a lot of debris and trash coming from this loading dock area. So how do we go and add in a worksheet for that? The way we do that is when we get to this step right here. So we go back and look at what we just filled out. We were focused on our swale in the first column. But for that pipe column, we could come in here and we could select yes for is pretreatment provided. And when we do that, it's automatically going to generate a new worksheet. And the worksheet name configuration is going to be a way to identify it's associated with this one. So as your site gets bigger and bigger and you have more outfalls and you have more SCMs, we want the workbook to know how to match up and pair individual worksheets. So we have our EDB at the eastern outfall. We're providing pretreatment through an HDS at node or design point E16 pipe. And so that worksheet name is going to be generated. So you've got your EDB, we've got our upstream runoff reduction inflows coming into the EDB. And at one of those locations, we're going to provide pretreatment using an MTD. And that's the worksheet we want to visit. So let's go jump into that worksheet and we'll look at what this new MTD worksheet looks like. So first thing is it's going to carry over your water quality event depth of 0.6 inches of rainfall. It's going to bring over the area and the imperviousness upstream of that inflow point. So what the loading dock area and part of that parking lot that are collected through the pipes, 96% imperviousness, roughly 22,000 square feet of area draining in. And what we want to do next is pick a runoff method because we're no longer looking at runoff volumes, capture volumes. For a hydrodynamic separator, we need to look at peak flows. And in the new chapter 6 of volume 1, the runoff chapter, there's information on how to calculate your water quality peak flow. And you can do that using either the rational method or the Colorado Urban Hydrograph procedure. Or if you've got some other research that's been done or another study that was formed, you may have another way of generating that peak flow. You can override it. So for the rational method, you need to provide soil type, and that's going to be used to help generate your runoff coefficient. You need to provide the length and slope of that flow path along with the conveyance factor. And that will give you a time and concentration, which you can then calculate intensity from. You'll get a runoff coefficient based on your imperviousness and soil types. and that will calculate your water quality peak flow. If you were to select CUHP as your runoff method, you would also need to provide soil types to help calculate your initial, final, and decay rate for infiltration. You need to provide your length of centroid along that flow path, and your average slope along that flow path. And then the program will assume default values for depression storage from the criteria manual. And once you click this button, Run CUHP, it'll run within this workbook, generate your water quality peak flow. And then the third option is if you have some other method of defining it, you can just provide your own override for the water quality peak flow. That will carry down. Once you've done that and you've generated your water quality peak flow, that's where most of the calculations are done for the workbook side. And we're really just utilizing this information from the SCM or from the EDB worksheet for that inflow location. The rest of this is really going to be answering questions based on information available from the manufacturer. So if we start working through that, we need to determine, is it an appropriate MTD? Is it appropriately sized for our water quality peak flow? So if we move to question number 2, we pick a manufacturer, a type, and a size of the device, and we evaluate, is the maximum capacity of that device greater than our water quality peak flow? If so, let's continue evaluating it. Have third parties verified that it is that it can treat that flow rate? Is it laboratory verified? Is it on the New Jersey Department of Environmental Protection certified list? What are the hydraulic loading rates? Is there a certification letter? All of this is information that you can obtain online to see if this is an appropriate device for your water quality peak flow. And then you can go further. Is it a good type of device for your site? Does it meet the characteristics of the site? Is it dealing with the targeted pollutants, whether that's trash, debris, oil, grease? What are the things you're trying to target? And is this device good at treating those? Does the configuration of the inflow and outflow match your site? So if it's coming in and leaving at a 90-degree angle, does that work with your actual site? Answer some of these questions to make sure it's an appropriate device. And these continue. Are there internal flow components? Like, are there baffles and weirs? How are those accessible? Do they need to be replaced? Is there access into the storage chamber? Is it large enough? How often is maintenance going to be needed? Is there an internal bypass? So if an event larger than your water quality peak flow happens, how does that flow move through the system? Does it flush everything back out, or does it have a bypass method? Is that internal or external? Look at your hydraulic grade line, energy grade line. Make sure that downstream conditions don't create a backwater effect that causes water to back up into the system, potentially, taking all that trapped sediment or trash or oil and causing it to be released because of the downstream conditions. Can you get to everything to maintain it? And once you've answered all those questions, you'll have a pretty good sense of whether or not this is an appropriate MTD. Is this appropriate type of MTD for your site, for your conditions, for your grade on your site, for the configuration of your inlet and outlet? And if so, great. If it's not, you may want to start back over, pick a different device, and work through those questions again. So that is how the new MTD worksheet for hydrodynamic separators is set up. And it's very similar for the high rate filtration MTDs as well. Some different questions because not all of them apply. But similar approach where you define your water quality peak flow, you pick a method, rational or CUHP, and then you kind of go through and answer the appropriate questions for that device. So once you finish that, it's important to know that there's nothing really to be carried back. What you've brought over from the EDB worksheets and those inflow locations is an area and an imperviousness. You're then going to generate a runoff, a water quality peak flow from that tributary area information, length, slope, travel time, whatever you need to generate flows. But the rest of this is really just looking at guidance from the manufacturer and seeing if their device is well suited for this application. There's really no information. There's no credit for volume reduction to get carried back to the SCM worksheet. So it's kind of that one-way arrow that we talked about earlier. Okay. And to wrap things up here, I want to kind of go through the whole site. What we did was we focused primarily on this Outfall E, and even then we focused primarily on this flow path from the roof and the parking lot through the swale. We talked a little bit about this additional parking lot, E19, draining across the buffer E20, when we started looking at the total runoff volumes into this and the 5 different inflow paths. So we had the piped inflow, we had this inflow, we had the SPA around the edge and this little SPA, and then we had our swale. So we talked a little bit about this, but your site may be much bigger. And in this case, sorry, let me jump back. We have a lot of different locations. Here we have a big parking lot area that drains directly to a sand filter before it's discharged off-site. So we've got an SCM here, different type. So we got EDB on the eastern, SCM on the northeastern. We've got on this lower corner here, we've got SPA, so just vegetated area. We've got a sidewalk draining across the grass strip before it hits the road. Same here. UIA RPA pair for the sidewalk. Same here, same here. So these, we're using the runoff reduction standard. We're just trying to infiltrate any runoff from the sidewalk before it reaches the street. Hopefully we can minimize any runoff that reaches the street in the water quality event. We've also got a rooftop here that's draining down through a grass buffer before it reaches a bioretention facility. Here we've got 2 different rooftop systems for evaluation, a green roof and a blue roof. We also have some areas that drain off-site directly. So you've got this driveway entrance in this parking lot. That's draining off-site without any treatment. Same thing here. This area drains off with no treatment. Same thing here with number 9. So what we're trying to do is look at all these various outfalls and figure out what is our overall site condition and are we meeting our water quality standard. So again, we focused on that eastern outfall for the EDB, and we met that through the water quality capture volume standard. If we look at some of these others where there's just runoff through RPA, we're trying to meet that through the grass buffers and the sidewalks. We've got a green roof and a blue roof. Green roof, you're getting 100% runoff reduction. On a blue roof, you're capturing that runoff volume. You're meeting the water quality capture volume standard by discharging it over 12 hours. Here you've got bioretention, and here we're trying to do full infiltration of that volume, no under drains, and so that part of the rooftop drains down through a buffer and into a bioretention facility. And then we had our sand filter in the northeast corner. And so all of this is described in more detail built into the workbook as the example. So you can kind of scroll through that and look at it in more detail. But in looking at the results, what I want to highlight is that with all of these outfalls, and again, we focused on this one, the EDB, we have some here where we've got runoff leaving that's untreated. So we may have had some runoff reduction credit through the buffers, but we still got runoff leaving the site untreated. And what the information in the summary does is it takes all these individual columns, adds them up. So we have a total site area of 7 acres. We are treating about 6.6 of that, and we've got about 0.4 acres that we're not able to capture. Those are some of those driveway entrances that are leaving undetained, uncaptured, and untreated. And so that's information that both the engineer and reviewer can use to determine whether or not you've met some of those exclusions for the permit. We also can look at what is the default water quality capture volume. And after you account for this water quality capture volume reduction due to infiltration and runoff reduction, like the green roof, you've taken all that runoff or you've essentially captured that in the green roof system, and that's being evapotranspired. So you have no runoff from that. So if you add all that up, we've got a total of 20% reduction in our original required water quality capture volume. Through the use of the bioretention and the EDB and the sand filter, we've included a total design water quality of 4,400 versus the 6,500 based on the default equation. So you can kind of see where that credit comes in. And then we have some that's leaving untreated. That 808 cubic feet is leaving the site untreated. That's from those areas that are hard to capture and redirect. So in summary, this is the information that you're going to end up with all of these different outfalls, getting credit for all of that different water quality capture volume reduction. And this is the information that both the reviewer and the engineer can use to determine if your site has met the standard and make those decisions. And with that, I am done, and I'd like to open it up for any questions that people have, either on this presentation or on something that maybe we didn't cover. Thank you.